We spent a lot of time figuring out how to get into orbit, but what do you do and where do you go once you're up there? Welcome back to the Upward Bound series, and I am your host, Isaac Arthur. We started this series almost a year ago and have discussed many different ways of getting into space cheaper and safer, and it's fairly impressive how much launch costs have dropped just in this last year alone. We, and a lot of other folks, have long predicted there would be a point where technology dropped launch costs while increasing what we could do up there that would result in a snowball effect. And I feel pretty confident at this point saying that I think we are seeing the beginning of that now. As it gets cheaper to get off Earth, we also have more things we can do up there, starting up a real economy and infrastructure in orbit, and I thought we'd spend a couple episodes discussing those options. For today, we will be looking not just at an improved space station to replace the ISS, but a genuine spaceport. Designs for those go a long way back, at least to von Braun's inflatable space wheel, and we started seeing the first realistic ones hit the silver screen in Stanley Kubrick and Arthur C. Clarke's classic film 2001: A Space Odyssey. Many more have been dreamed up since, and we have discussed some very large ones we can build down the road, but I was curious what folks had come up with in recent years, tailored to the current and emerging technologies. As I investigated those, I ran across the Gateway Foundation's Orbital Assembly project and got to talking to one of their engineers, Kit Carson, and their president, John Blincow. One of the cool things about running this channel is getting to chat with all the aerospace companies working to bring the future about, and a lot of them tend to be big believers in a lot of the ideas we discuss here, and it is fun to pick their brains and bounce ideas around. There are a ton of options for our first spaceport, but it's easier to focus primarily on one design, since Gateway has a Kickstarter coming up for drone assembly robots to be used in orbit, and was kind enough to lend me their top-notch animations of some of their designs. I thought we'd use theirs, though I'll admit their option to go big for that first spaceport also swayed me. Most plans lying around amount to a space station upgrade not much bigger than a house. They are thinking gas station or maybe freeway truck stop, not airport. And a lot of times they're not including all the ancillary stuff we tend to see near such facilities: convenience stores, motels, hotels, restaurants, entertainment, and so on. We discussed a lot of systems that might get launch costs down to under $100 a kilogram, indeed for some just a couple bucks a kilogram, and SpaceX is set to bring that cost down to under $1,000 in the very near future with their BFR, a skyscraper-sized rocket. $1,000 a kilogram has been a fairly common figure to use as that snowball point, probably because it's about the zone where transporting a person into space is about the same as the GDP per capita in a developed nation, at which point going up to orbit is obviously still a serious luxury, but no longer restricted to billionaires. As of today, with nearly 60 years of missions to space, we still haven't even sent 1,000 people up there. We have a lot of airports that process that many people through every hour, and even the little airport near me, mostly for recreational flying, does that many in a week. If we want to be able to say that we have a genuine foothold in space, we need to be thinking about spaceports that can welcome 1,000 people a week. It is worth noting that even at that rate, that's only about 50,000 people a year, while still being nearly 100 times as many folks as we've ever sent up there so far. 50,000 a year would mean only 1 million people out of each generation of humanity got to go into space just one time. If we wanted everybody to get a chance to spend a week up there, it would mean sending not 50,000 people a year, but 100 million. That's 3 people every second, rather than about every month as now. Needless to say, that's a long way off, but if launch costs drop to the point where a person, and a little bit of luggage and supplies, call it 200 kilograms a person, could be sent there for $1,000 a kilogram, or $200,000 each, $10 billion would provide 50,000 people access to space. That's actually a very plausible annual figure for tourism alone, and there are a lot more than 50,000 folks who could afford that ticket. More to the point, it starts opening options for private sector spending we tend not to think about. If you want to rent out the Vomit Comet for a flight, it costs about as much as one of those tickets we just mentioned, and that gets a film crew a couple dozen zero-gravity intervals of about half a minute, spread over a few hours of flight. Not really ideal filming circumstances. Alternatively, a spaceport could easily have several bays just given over to filming, where a cast and crew of 50 could spend weeks shooting up there unrushed for a price tag of around $10 million, a sizable but hardly murderous cost for a big-budget film. That's also a pretty good draw for other folks in publicity, since a lot of folks would enjoy getting to meet celebrities up there filming, or get cast as an extra in a film, since it makes sense to grab those from folks already up there. And I'm sure you'd have a lot of video blogging going on by those celebrities while they were up there too. That's just one example of something that has nothing to do with science that you could use a spaceport for in the near future. If we want others, we really only need to consider what we tend to find at more conventional transportation ports. Hotels, restaurants, and casinos would be some examples. I was joking with John and Kit that someone might make a fortune patenting the first zero-gravity roulette wheel or magnetic table and dice for gaming. And for the same reason lavish charity gambling or dinner events tend to do well, these probably would too, since those doing it can point out that they are helping fund a good cause. That was actually one of John's more interesting ideas for funding too, a lottery where the winner gets an all-expense paid trip to the spaceport. Launch costs may be getting a lot cheaper, but we'd still be talking tickets priced at a decent fraction of $1 million, which is more than most of us will ever have to spend. But if you can buy a ticket, like with most state lotteries where a big chunk goes to education or similar, you've got a plausible shot at winning and knowing all that money is either going to fund making it cheaper and better, or sending someone up there. Don't think of this as a small additional source of potential funding either. Lotteries alone bring in over $70 billion a year in the US, about double America's total space program spending, not just NASA, and $300 billion globally, about 5 times what the whole planet spends on space programs. It would let us get a lot more science done, to the point where universities can afford to send a scientist or two up there for months, and rent out a lab all to themselves. Right now, it can take years just to get a small box up there that an astronaut might tinker with for a few minutes a day for you, and this is not ideal for a lot of experiments. The thing is, a spaceport that can handle several hundred people on board at once is not a small thing, and proportionally even bigger than the ISS, because folks will want more elbow room. The Gateway Spaceport design is modular, designed to be built in chunks and mostly automatically, and also expandable, and begin with the Gateway Assembly Line or GSAL. The GSAL is an automated assembly system designed to create segments of a structure. The segments are then welded together to form the whole structure. This method of construction is called permanent modular construction. The GSAL will consist of a number of workstations, each with a different assignment. Each will assemble semi-complete segments, much like aircraft manufacturers and shipyards do. You ship up the raw materials and it takes them in and spits out segments, like trusses. An interesting advantage of space construction is your trusses don't have to be all that massive, as there's no gravity to fight. You construct modularly in blocks. The GSAL makes square sections for the station hub or wedge segments for the ring sections. Beams go into the GSAL and modules come out to be welded into place. They estimate each block would take just under half an hour to make. The GSAL itself is roughly 12 by 12 by 120 meters, and the modules themselves can be a maximum of 7.6 meters wide and tall, or 25 feet, and can actually be of any length, but the default construction of the spaceport hub called for a length of 76 meters, or 250 feet. You can make segments skinnier, shorter, longer, or have them vary in width so as to produce wedge-shaped sections for a ring. Each one of these, using the default length for the spaceport hub sections, would be 7.6 by 7.6 by 76 meters with a volume of 4,400 cubic meters, almost 5 times the pressurized volume of the International Space Station at just 916 cubic meters. The Gateway hub section is a disk with a large rectangular docking bay cut into it, composed of a couple hundred of these modules. Its own pressurized volume is 1.1 million cubic meters, fully 1,200 times that of the ISS. And that's pretty darn big, true, but it's peanuts compared to some of the structures we talk about, even the modest ones like an O'Neill cylinder, but it would dwarf every object we've sent into space so far combined. Now, with a radius and depth of 76 meters and 1.4 million cubic meters of volume, both the pressurized section and vacuum exposed bay, you could stop here and have a very complete and useful spaceport. There's plenty of room for ships in that bay too. It's a good deal larger than a football field and is designed to operate standalone from additional segments. Of course, as big as it is, we will want to add some components onto the hub. Now, by default, a space station has no gravity, and as we discussed before, you can simulate gravity by spinning the object. How fast you spin it and how far you are from the center of the spin controls the apparent gravity inside. This apparent gravity is linear to the radius or diameter, so if you double the ring size, you'd double the apparent gravity. Alternatively, if you climb halfway toward the middle, you would have the gravity and it would be zero at the center. This is not the case for the speed the object is spinning at though. You can calculate this either as the tangential velocity, the specific speed the outside edge is spinning at, in which case the apparent gravity rises with the square, or with its angular velocity, the rate at which it is rotating. As an example, the Earth spins at the equator at about 460 meters per second, its tangential velocity, while it spins 1 revolution per day, its angular velocity. RPMs or revolutions per minute tends to be the default value spin gravity stations are given in, and it also causes a rise in spin gravity with the square of angular velocity. Hypothetically, you can simulate any level of gravity this way, but it puts a huge strain on the station to hold together the larger you make it and the faster you spin it. On top of this, people don't handle being spun around rapidly in circles too well. It makes us nauseous and disoriented. It's generally accepted that anything less than 2 RPM won't bother people, and we've some indications that with training we could get used to a good deal more. Now, one of the reasons we don't have such a spinning section on the ISS is that we've got plenty of places to do gravity-based experiments, but just that one small station for zero gravity. Plus, the place is small enough that any rotating section would either have very little gravity or be nausea-inducing. The Gateway Spaceport aims for something much larger. Multiple rings with much larger diameters spinning will be slower. The first to be built and the innermost of these would be the Lunar Gravity Area or LGA with a radius of 152 meters. By rotating once per minute it would generate 17% of normal gravity, the same as on the moon. Needless to say, this would be handy for folks training for moon missions, which is why that was selected. For a Mars gravity area, a ring with a larger radius would simulate Martian gravity, or lower, to simulate a place like Jupiter's moon Callisto, which only has 13% Earth gravity, and as we discussed in the Outward Bound series, is one of the best potential forced bases for humanity out past the asteroid belt. However, besides training, its real advantage is allowing us to do long-term studies of the effects of low gravity on people. We actually have no idea what that is. The 12 folks who have ever experienced low gravity only experienced the moon's specific value, and only for a few days. For all we know, even the moon's small surface gravity might be entirely enough for healthy people to live years at a time, or it could be that even Venus's near-Earth gravity isn't enough. Best to find out in orbit, now, not in the middle of a mission millions of kilometers from help. This is important too, as for instance we have no idea how much gravity is needed to safely carry an infant to term, and we've good cause to think that it is a gravitationally sensitive process. You've got serious issues colonizing other planets if you can't, well, manufacture colonists in situ. And if there are any complications in pregnancies from gravity, it behooves us to identify them on some large and well-equipped space station close enough to Earth for real-time communication, not on some cramped moon base or Martian colony. So the LGA lets us investigate the long-term effects of lunar gravity and train and prep crews for missions to the moon. It also allows folks to enjoy the fun of low gravity while still having the intuitive sense of up and down work. The plans call for 300 guest rooms, which would have the advantage of allowing you to sleep without needing to strap in and drink from normal cups rather than bulbs, and avoid the unpleasantness involved with using the restroom in zero gravity. I suspect a lot of folks would want to try out the full zero gravity experience, but after a day or so might be glad to have a room with some gravity in it. And the LGA has plenty of rooms in it. At 3.2 million cubic meters of volume, it would be 3,400 times as spacious as the International Space Station. The next ring to be built would be the MGA, Mars Gravity Area. With a radius of 244 meters, it would only simulate 27% gravity at 1 RPM. Mars is actually at 38%, so we would have to adjust spin to 1.18 RPM. Again, well beneath the 2 RPM value we think is safe against disorientation. Spun to 1.9 RPM, it would match normal Earth gravity, and a bit less could simulate Venus. At 30 meters width, which would be several floors or decks, and 45 meters depth, the LGA would have a volume of 2.2 million cubic meters, about 2,400 times the volume of the ISS. It would also include 46 megawatts of solar power generation. This ring is expected to house about 1,000 people spread over 550 guest cabins, and is viewed as more of a long-term residence area. A mission to Mars calls for 18 months on the ground in Martian gravity, so we need long-term tests to begin with, so it is anticipated this area would also include apartments or facilities for rent or lease. Probably fairly expensive, after all, if you are only including launch costs for supplies, and totally recycling air and water, supplies for one person for a year might easily still run $1 million. But that is viable for crew or long-term researchers, or folks who are quite wealthy and simply want to live in space. Space in space is actually fairly cheap and made cheaper by the square cube law, as we discussed with larger spaceships. If you simply double something in size, its surface area rises by the square, or 4, but its volume rises with the cube, or 8. You need 4 times the shielding and hull material, but you get 8 times the space inside it, or need only half the shielding per unit of space. As mentioned, the hub is over 1,000 times bigger than the ISS in volume, so essentially it only needs about 1/10 the shielding material per unit of space as ISS does. You wouldn't want to be lavish with room design, but your bottleneck is on the mass of furniture and equipment in a room more than the size of the room. You could have a couple thousand people living, working, or visiting the full Gateway Spaceport at any given time, with shuttles carrying 30 to 40 people arriving and departing several times a day. And that's just the default size of the station. You can make it skinnier or wider, and the GSAL is basically printing those modules like pasta. You can cut the module noodle at any length. You could also build a whole other spaceport instead if you need room, in a different orbit or right next door, and connect them. Now, a big aspect of construction is going to be drones, and you basically have 2 types, the flying kind and the crawling kind. The latter zip around welding things. Welding in a vacuum is tricky, but we've had some practice. And the other kind mostly zips around grabbing things. We really don't want tools or construction material wandering off, both for the loss of material and because a hammer that spins away at 1 meter or 2 a second is still actually moving several thousand meters per second relative to Earth, and could eventually smash into something on a different orbital path with a huge amount of force. Indeed, next time in this series, we'll be examining how that can cause a runaway effect, where objects get destroyed, their debris scatters and destroys more things, and so on, littering orbital space with millions of hypervelocity bullets and potentially preventing any space travel. This is known as Kessler syndrome, and we will discuss it in more detail, along with ways of handling it, in the next episode of the series in a few weeks. Those drones could be controlled by station operators, but in fact, seeing as how the station is only hundreds of kilometers up, ground-based pilots could control them, saving a lot of money. Indeed, if our robotics get good enough, you could use humanoid-shaped robots, like NASA's Robonaut, piloted by folks in virtual reality down on Earth, potentially allowing a much bigger crew who also don't need living space or time off, as the next shift just takes over the robot. For manned construction, we have something usually called a pod, which is basically a small pressurized vehicle, though the person inside would likely wear a suit anyway, with various jets to move it around and arms to manipulate equipment and tools. And of course we'd have classic spacesuits for EVA too. Spacesuits remain a problem as they are bulky and leak, and more the higher the pressure, hence why we tend to use oxygen only in spacesuits and have to have the astronauts pre-breathe to purge the nitrogen from their blood. One of the preferred ways to deal with this is a rubberized suit that would push on the wearer, but we have problems at the neck and helmet interface, partially because while you can squeeze a body fairly hard, you can't really squeeze someone's neck that much, as it tends to make them pass out and die. Hence, pods and drones are going to be preferable, and our technology there is rapidly improving. The thing about a spaceport of this size is it allows you to have a crew big enough for lots of specialization and redundancy, while also allowing lots of folks who have nothing to do with spaceport operations, including crew members just there to monitor those visitors or residents so they don't kill themselves on accident, and provide hospitality of course. You could easily have small teams from dozens of universities or government labs conducting experiments up there, while movie crews film and travelers come by just to enjoy zero gravity and all the various associated entertainments we could come up with, like a zero-G racquetball court or casino. And since it does have gravity in segments, you've got places for people to go if that lack of gravity gets overwhelming, since you'd doubtless be screening everyone medically before they went up there, and when they got home, you would also build a very large data pool on health effects of no gravity and low gravity. You've got room for entire hydroponic gardens for botanists to work with to do large samples of mini plants and see how low or no gravity affects them, instead of small terrariums like we are limited to now. We can also do some zoology too. We haven't taken that many animals to space, especially large ones, or done much research on how groups of them behave in the long term. What changes to hunting or breeding might occur in low gravity? How would a flying squirrel act in a forested dome with lunar gravity? Folks heading off to a moon base will have had time to get used to the gravity and will know there's a platform with ships docked to it, and fuel that could resupply them rapidly, no weather-fickle ground-based launch windows, and come get them in an emergency. We can train Mars crews safely for simulated 26-month missions, part in no gravity and part in motion, and see for sure if they can handle it before sending them off where we can't help. Asteroid mining companies could know they've got a place to dock and unload, refuel, repair, and get some relaxation before heading off again. You could have repair bays so that potentially a satellite could be repaired, or even assembled from parts, right there, rather than needing to design it for fitting into one rocket payloads, and eventually being pushed up to a graveyard orbit or down to burn up. If your 3D printing is good enough, you could manufacture replacement parts or upgrades right there. And if your robots are versatile enough, the work could be done there with them piloted by expert technicians who are groundside controlling the robots. Once you build your initial space construction infrastructure, you could start assembling truly huge space-based telescopes too. Remember, Hubble is pretty big, but there are many ground-based ones that are larger, and you can actually make bigger ones in space. Tons of options, and more will emerge after such a spaceport is created too. If you build it, they will come. And once the hub is overloaded, you build the LGA segments, then the MGA. Then you can add on more independent modules attached to it, or a whole new station connected to it or serving a different orbital path. The Gateway Foundation spaceport design is not the only one, but it especially impressed me, as did their work on drones, which we'll be looking at more next time in the series. More so because it's not just a design for one space station, but a setup designed to be able to continue perpetual construction of new ones, so we can accommodate more and more people and keep dropping the price tag to go up there, until eventually the available space rises and the costs drop so that anyone can go. They do have a Kickstarter just opening up for the drone design, and I will attach a link in the video description if you want to read more and support them. And I know they are also looking for crew members and volunteers to help out on the graphics side, much like us here at SFIA, where I am also always looking for folks with some computer graphics skills and time to volunteer them. Those animations are not core to the technological development, but they are vital to explaining these concepts to folks and helping gather interest, enthusiasm, and of course funding. And again, if you want to help them out in either way, I'll leave the link below, and hopefully we'll get some good space drones out of it in the near future, which will be vital to infrastructure in space. At this point, with even just the completed hub of the spaceport, you do have the beginnings of a basic orbital infrastructure and the perfect beachhead to expand that. We will be looking at orbital infrastructure, more on orbital construction, and as mentioned, orbital debris and Kessler syndrome in 3 weeks. Before that, we will be heading back to the Fermi Paradox series to examine the concept of ancient hibernating civilizations in Fermi Paradox Sleeping Giants. And then we will launch off to Alpha Centauri to discuss colonizing the system and look at the special difficulties of binary and multiple star systems. For alerts when those and other episodes come out, make sure to subscribe to the channel. And if you enjoyed this episode, hit the like button and share it with others. You can also discuss these topics with like-minded individuals in the comments below or at our Facebook and Reddit groups, Science and Futurism with Isaac Arthur. Until next time, this is Isaac Arthur saying thanks for watching and have a great week.